All right, let's jump right into this explainer. We often think of data modeling as this tedious, behind-the-scenes chore, just something you have to slog through before getting to the fun part of building dashboards. But based on the enterprise reference manual we're unpacking today, we really need to flip that mindset entirely. Data modeling is the absolute bedrock of your enterprise business intelligence. And honestly, it's the strict, non-negotiable prerequisite for AI readiness. If your model is structurally weak, well, literally everything built on top of it is going to crumble.
So let me ask you a question, and think about your own organization for a second. Why do your reports completely crawl when you try to apply a simple filter? Why is the data suddenly inaccurate? Or why is your finance team pulling their hair out over 14 different totally conflicting revenue figures for the exact same month? It's incredibly frustrating, right? You might instinctively blame a poorly written DAX calculation or maybe a visual that's just trying to render way too many data points.
But here is the kicker. A staggering 80% of Power BI performance and accuracy problems actually stem from poor data modeling decisions. Yep, 80%. Not the visualization complexity, not DAX errors. A well-designed semantic model literally eliminates entire categories of analytical failure before they even have a chance to happen. That means investing time in your modeling quality is hands down the highest ROI technical decision you can possibly make.
So, to get us to that elite level of quality, here's our roadmap for today. 1. The data modeling imperative. 2. Building the star schema. 3. Optimizing the VertiPaq engine. 4. Enterprise security and scale. And 5. The AI native future.
Let's start with Section 1, the data modeling imperative. Moving past those visible symptoms and getting down to the structural fixes. Right at the heart of so many failing BI systems is this fundamental architectural conflict. On one side, we have OLTP, online transaction processing. These are your operational source systems, like your ERP or CRM. They're highly normalized and engineered for fast, reliable writes. On the other side, we have OLAP, online analytical processing. That's what Power BI is. It is deliberately denormalized and read-optimized for lightning-fast aggregations. Hooking up an OLAP engine directly to a highly normalized OLTP system is a total category mismatch. They have entirely opposing optimization strategies. It's like trying to win a Formula One race in a dump truck.
Which brings us to Section 2, building the star schema. This is the foundation of your analytical performance.
To avoid importing some sort of Frankenstein operational model directly into your reporting layer, you absolutely must define your grain first. Grain is simply the lowest level of detail represented by a single row in a fact table. Listen, this is the single most critical design decision you are going to make. Almost every analytical error caused by a bad fact table traces right back to a fuzzy or poorly defined grain. Mixing different granularities in one table, like shoving daily sales and monthly targets into the exact same table, is a massively destructive anti-pattern. You have to explicitly define that grain from day one.
Once that grain is set, the whole game is about strict separation. Notice the very clear division of labor here. Your fact tables, they hold your numeric measures, the hard quantitative data. They are incredibly narrow, usually just packing foreign keys and numbers, but they have a massive row volume, easily stretching into the billions. Dimension tables, on the other hand, exist to provide descriptive context. They are much wider, full of text and categories, but with far fewer rows, and they always feature a unique primary key. The golden rule here, you filter on dimensions and you aggregate on facts.
Now, speaking of dimensions, we've got to talk about the date table. It is an unbreakable architectural rule that a dedicated date table is mandatory. Relying on raw date columns inside your fact tables for time intelligence is just a recipe for disaster. We can all poke a bit of fun at the hidden terrors of Power BI's auto-date/time feature, right? It quietly creates these hidden tables in the background that silently bloat your model and tank your performance. A dedicated marked date table with a continuous sequence of dates, and I mean 0 gaps allowed, is completely non-negotiable for accurate time-based analytics.
Moving on to Section 3, optimizing the VertiPaq engine. Let's take a look inside that high-performance engine room.
The VertiPaq in-memory engine is insanely smart. During model processing, it automatically chooses one of 3 encoding strategies for every single column. You have value encoding, which is used for numbers with a tight range, giving you blazing fast, direct arithmetic. Then there's hash encoding, which builds a dictionary lookup for text or high cardinality data. And finally, run length encoding, or RLE, which achieves maximum compression by just skipping over entire runs of sorted, repeated values. Now, even though VertiPaq chooses these automatically, if you understand what triggers them, you can engineer massive size reductions just by tweaking your data types before import.
To really put that into perspective,
Check out this real-world benchmark. Look at that order ID column stored as a text-based GUID string. Across 50 million rows, it compresses at a pretty pathetic 1.3x ratio, chewing up 1,850 megabytes of memory. But if you just convert that string key into an integer surrogate key, like the product key example, it triggers value encoding. Suddenly, you're getting a staggering 42x compression ratio, shrinking down to just 4.8 megabytes. On a massive enterprise dataset, that one simple data type change saves over a gigabyte of RAM. It's literally the highest ROI optimization you can do.
Section 4. Enterprise Security and Scale. Because we have to operate in production reality. So, when it comes to row-level security, or RLS, there is a very clear right and wrong way to do this at scale. The anti-pattern is static RLS. It relies on hard-coded DAX filters. Think about it. If you add a new region or a manager changes teams, a developer literally has to open up the model, manually edit the roles, and republish the whole thing. It completely falls apart at enterprise scale. Dynamic RLS, though, that is identity-aware. It uses the user principal name function to check who's logged in against the security mapping table in your database. When new users join, you just update the data table. The security scales infinitely, and you never have to touch the model itself.
And to keep all that data fresh without completely melting your servers, we rely on incremental refresh and hybrid tables. Obviously, you can't run a full refresh on a billion-row table every hour. Instead, you partition it. The real magic of hybrid tables is that you can blend frozen historical data, stored in that blazing fast import mode, with a real-time direct query partition for whatever's happening today. To the end user, it just looks like one seamless, lightning-fast dataset. But under the hood, the engine is smartly routing subqueries to give them historical speed right alongside to-the-minute accuracy. Finally, Section 5, the AI-native future. Let's look at the ultimate stakes for your data foundation.
There's this fantastic concept in the source material called the AI amplification effect. The idea is that AI doesn't actually introduce new risks to your data. It just completely obliterates the human friction that used to slow down the spread of those risks. So if you feed Copilot or an LLM an ungoverned, messy semantic model with poorly named columns and totally conflicting metrics, the AI isn't going to magically fix it for you. Actually, scratch that, it's worse. It will confidently generate hallucinations, fake KPIs, and wildly incorrect correlations, and serve them up at conversational speed to every single user in your company.
So how do we actually prevent that chaos? We use a retrieval-augmented generation, or RAG, architecture built specifically for BI. Look at how this flows. First, a user asks a natural language question. But crucially, in step 2, the AI agent doesn't just guess. It retrieves metadata strictly from your certified, pristine semantic model. Then, the LLM generates a query that is constrained entirely by that specific schema, meaning it physically cannot invent table names or fabricate metrics. And finally, the engine executes the query with all your dynamic row-level security fully intact. A clean semantic model is exactly what grounds these AI agents and prevents those dangerous hallucinations.
Which brings us to the bottom line. The AI revolution in business intelligence isn't really about who has the fanciest generative model. It's about who has the most disciplined operational systems. Excellent BI and trustworthy AI require the exact same foundation, a governed, documented, and well-modeled semantic layer. So I'll leave you with this challenge to take back to your team. Take a hard look at your schemas. Look at your grain definitions. Look at how your security scales. Is your enterprise data foundation truly ready for AI? Because, let's face it, the future of analytics isn't waiting.